We're going to look at the chemical properties of alkenes. We're going to look at the chemical properties of alkenes. But we know that alkenes are nucleophiles. The reason why they're nucleophiles is because they possess the carbon-to-carbon double bond. Remember what we said? That the double bond, a bond, a single bond is a pair of electrons. Meaning, if it's a double bond, that is two pairs of electrons. So, we have a high concentration of electrons between carbon and carbon atoms. Because of this high concentration of the electrons, these electrons tend to always attack electrophiles. What are electrophiles? Electrophiles, as we know, these are electron deficient species. If a species is positively charged, then it lacks electrons. Do you see that? Some electrophiles just have empty orbitals such that they can be able to accommodate electrons coming from any electron-rich species. Therefore, if we talk about electrophilic addition, we are just simply saying that an unsaturated alkene can get more atoms. These atoms should be electrophiles into their carbon skeleton. Do you see that? For example, if we have a carbon-to-carbon double bond here, we are saying this double bond can be used to create a bond between other atoms that can be incoming in a compound. So that means that all the reactions that we are going to look at for alkene, they are all going to be addition reactions, whereby an electron deficient species is coming in to join the skeleton of an alkene across the double bond. And we are saying our first reaction is the hydrogenation of alkenes. Hydrogenation of alkenes. So hydrogenation, as the word sounds, comes from the word hydrogen. We are adding hydrogen across the double bond. We are saying alkenes react with hydrogen in the presence of the catalyst. Now we have three options of the catalyst that we can use. We have nickel at 150 degrees Celsius, or we can use platinum at room temperature. We can also use palladium at room temperature. These three catalysts, each of them can help us to add hydrogen across the double bond. So in our illustration, we're going to use a general representation probably of the what? A general representation of a double bond, of an alkene. This is a general representation of an alkene, probably in that case, where R can stand for any alkyl, ethyl, methyl, it can become a branched alkyl. It just doesn't matter. So in this case, I am adding hydrogen. Of course, hydrogen is diatomic, and I'm saying I can use in presence of a nickel catalyst at 150 degrees Celsius. Nickel catalyst at 150 degrees Celsius. This hydrogen is going to be split into two atoms, and these atoms are electrophiles. Each shall be added across the double bond. That means we are going to end up with RCH2. Of course, the double bond will be dissolved, leading to the formation of the additional hydrogen here, and then we shall have again CH2R. So this is hydrogenation. We are adding hydrogen atoms across the double bond. To just pick a clear example, maybe I can illustrate it here. We can have CH2, CH, double bond, CH2. That this one. So if I add hydrogen across, I'm adding plus H2 in the presence of the catalyst. This time I can select use platinum at room what? At room temperature. Platinum at room temperature. So hydrogen is going to be attached here and here, leading to the formation of CH3, CH2, CH3. I've added hydrogen atom here and a hydrogen atom there. So, in most cases, when you hydrogenate an alkene, you lead to the formation of alkenes. Because you are trying to eliminate the double bond. So the alkane and then the hydrocarbon that is formed as a product lacks a double bond, and that means it is saturated, and the unsaturated hydrocarbons. Okay, yeah, so that is it. So every time you have an alkene, you can always hydrogenate it by adding a hydrogen atom across the double bond. So our second property, chemical property, we are looking at halogenation of alkenes. Halogenation, like the word sounds, comes from halogens, and halogens are group 7 elements. Therefore, these halogens can be added still across the double bond, just like hydrogen. They can be added across the double bond. And, but we are going to be also specific to say that we are going to use only chlorine and what? And the bromine. Why? Because iodine is not going to take part in the reaction in that way. And also we are also saying that it must be in the presence of a solvent called carbon tetrachloride. It's going to be in the presence of carbon tetrachloride. So I'm going to illustrate it. For example, if we have CH3, CH double bond, CH2, CH double bond, CH2. So I'm going to add chlorine. In the presence of carbon tetrachloride. This is the solvent that is going to stimulate the reaction between chlorine and the alkene. Which alkene now here has 3 carbon atoms, therefore it is propene. So what will happen there? Since halogens are diatomic, that means we have 2 atoms of chlorine, and these 2 atoms are going to be distributed to the adjacent carbons across the double bond. So we shall end up forming CH3, CH, then CHCl, then this is going to be CH2Cl. I think you can appreciate that. And now this is a dichloride. Why do we call it a dichloride? Because there are 2 chloride atoms on the carbon chain. There are 2 chloride atoms on the carbon chain. So what name will we give this compound? First of all, we have to appreciate that there are 3 carbon atoms. That means that is going to be a propane, since there is no double bond. So it is going to be a derivative of an alkane. But now the position of the chloride here is carbon number 1. This is carbon number 2, right? So we are going to say 1, 2, then dichloro-propane. So when we are attaching the numbers on these carbons, we are going to start from this side. 1, 2, 3, We cannot begin from this side, because if we begin from this side, then this will be position 2 and 3. We cannot say 2, 3 dichloro. It has to be 1, 2. So the smallest positioning determines where to begin from to attach number of the carbon atoms. Dichloro, di, meaning 2. So that's why I have said that this reaction leads to the formation of dihaloalkenes. Now let us try to suggest the mechanism for this reaction. Let's try to suggest the mechanism for this mechanism. So under our mechanism, we are saying we are going to begin with our alkene CH3, CH double bond, C, H2, double bond CH2. Do you see that? Double bond CH2. So we are going to attach. Our chlorine. So I'm going to express chlorine in this format. Why am I doing that? Now, the reason why I'm doing that is because first of all, chlorine is diatomic. Secondly, I want to create an electrophile here. How am I going to create an electrophile? One thing you must appreciate, the chlorine bond is a covalent bond. Is that okay? A covalent bond. But at some point, there are what we call partial charges. Because sometimes these electrons, when we bond into electrons, they can be this side. Do you see that? Causing this one to be partially negative. They can be towards this side, causing this chloride to be a partially negative. And a partial negative induces a partial positive heat. This is common especially for covalent compounds, which bond via what we call van der Waals forces. So the chloride atoms, chloride molecules bond by van der Waals forces. Do you see that? So in most cases, these electrons, when they are inclined towards this chloride, it induces what? A partial negative charge. This chloride, because the concentration of the electrons are more here, inducing a partial positive heat. But this happens in a very small time. Because on a good day, the electrons are supposed to be evenly distributed on the bond because they are identical atoms with the same electronegativity. But it is possible that at some minute second, this one becomes negative, inducing a positive here. Now this would induce a positive on the next atom, partial positive. Remember, this is the van der Waals force that is connecting this molecule to this molecule. If this one in a moment becomes negative, it induces a positive on the next guy here. And this next guy becoming positive induces the negative here. But still it is possible that this becomes negative, this becomes positive, and vice versa. So this is very common. Someone is going to say, since they are the same atoms, why do we have partial charges? Partial charges are very possible because of the distribution of the electrons across that bond. In a moment when this one becomes partial positive, we call it an electrophile at that moment. And the double bond will not hesitate to attack it. Do you see that? Because the double bond is a site rich of electrons. So the moment this chloride becomes positive, it will be attacked. When it is attacked to be taken off, then the chloride, this chloride uses partial negative, will take the chance to take away the chloride. To take away, the bond. That means the bond will be broken. The question is, this double bond, when it is taking away the chloride, where will it take it to? That is the question. Will this chloride be attached to this carbon or this carbon? That is a good question. The answer is there is a man called Makonikov. Makonikov. This guy came up with a theory that says that if you want to add an atom across a double bond, it is going to be attached to the carbon with more hydrogen atoms. With more hydrogen atoms. So it means this chloride that is coming across the double bond is going to be attached to the carbon with the more hydrogen atoms. That means they are going to form CH3, CH, CH2CH. This chloride has been attached to this carbon with more hydrogen. And because of that, now this carbon here has lost a bond. And because it has lost a bond, it will become positive. Remember we say a bond is a pair of electrons. So it has lost an electron. So it becomes positive. So this chloride here, it has been lost minus the chloride. Do you see that? But this chloride, because it has been lost, it is still what? It is also negative. It is negative. And because it is a negative, it's going to be attracted to this carbocation. So when it is attracted, it will come and do what? And attack. That's it. Carbon, which is positive, leading to the formation of CH3, CH, Cl, then CH2, CH2Cl. It is important to follow Markovnikov's rule when you are doing this mechanism. You don't just add the chloride across the double bond. Unless the double bond is shared by carbons with the same number of hydrogens. So there you can attach the chloride anywhere. But if the carbons have different number of hydrogen atoms, then the chloride or any atom that is incoming will be attached to the carbon across the double bond with more hydrogen atoms. Do you see that? Later we shall look at what we call the anti-Markovnikov's rule. We shall look at the anti-Markovnikov's rule later, whereby the atom coming in is attached to the carbon with less hydrogen atoms. Let's look at a second example. We can use our second example. I can have CH3, CH double bond, CH, CH3. This is built because they are 4 carbon atoms, built, but the double bond is on carbon number 2, so it is built 2E. So I'm going to use bromine in presence of carbon tetrachloride. So we have that. So I expect the bromine atoms to be attached across the double bond. So that will be leading to the formation of CH3, CH, Br, CH again, Br, then CH, CH3. What name would you give to this compound? So if I begin from this side to count, to give carbon atoms numbers, this will be carbon number 1, carbon number 2, carbon number 3. So the bromine atoms are carbon number 2 and carbon number 3. So it becomes 2, 3 dibromo. The whole thing is an alkane. So it's the derivative of an alkane with 4 carbon atoms. Therefore, we call it butane. Remember, when you are writing, it is 1,1. So do not separate dibromo and butane because it is 1,1. Let us look at what will happen at the mechanism there. So under our mechanism, we are having CH3, CH double bond, CH still CH3. But remember we are having our bromine molecule, which is diatomic. We have said that this one is also a covalent molecule, whose molecules bonds combined by van der Waals forces. Therefore, it is possible for this to become partial positive and this one become partial negative due to the uneven distribution of the electrons shared here in just a microsecond. When that happens, the double bond will attack the atom that is positively charged. The one which is negatively charged will take an opportunity to break off. So in that case, we are losing the bromide and the bromide ion. So this bromine atom that has been attacked is going to add itself to any of the carbons here, since they all have the same number of hydrogen atoms by McConaughey. I hope you remember that. So this one can either come here or here, since we have the same number of hydrogen atoms with each carbon, leading to the formation of CH3CH. So I can attach it here, Br, then this one would have lost an electron because the double bond has been used to create a bond between carbon and bromine. So it will become electron deficient positive, CH3. The moment it becomes electron deficient, then this bromide ion that has gone away with an electron will seek to attack it. So when it attacks it, that will lead to the formation of CH3, CH, Br, CH, Br still, then CH3, then CH3. So we are going to form that compound which I actually call 2,3-dibromo. 2,3-dibromobutane. Okay, now we want to look at our chemical property of alkenes. We are calling it halohydration. Of alkenes. Like the word sounds, halohydration. Halo, addition of hydrogen, halogen hydration, that is water. So we are saying that chlorine and bromine react with alkenes in presence of water to form chloroalcohols and bromoalcohols respectively. So the second property that we have just looked at, we are adding a halogen in presence of carbon tetrachloride, or you can call it tetrachloromethane. So in this case, we are changing from carbon tetrachloride to water. And the moment the solvent changes, even the product will do what? Will change. I.e., a good example, we can have CH3, CH, double bond, CH2. We are adding, maybe in this case we can add chlorine in presence of water. Chlorine is diatomic in presence of water. We are changing, instead of using tetrachloromethane, we are using water, and then we are saying we are going to form an alcohol, whereby one of the chlorides will be attached here, and then the OH from water will come and be attached here. So we shall form a CH3, CHOH, and then CH2Cl. And we are going to see how this one comes about. Let's suggest the mechanism. So under our mechanism, we are having CH3, CH, double bond, CH2. So we are beginning molecule, which is going to split into two chloride atoms. This one will be at some point partially negative, this one partially positive. So this one will attack the positive one, and then the negative one will break off. So when it breaks off, what do we have? We shall have this chloride. Remember, by mechanical, we said it's going to be attached to carbon with more hydrogen atoms, leading to the formation of CH3CH, then CH what? 2Cl. Of course, this one will now be forced to be positive. This force to be positive. Now, instead of like in the previous mechanism, whereby the chloride is now going to attack the carbon with the positive, in this case it will be the water molecule that will be attacking. Why? Because the oxygen on water has lone pairs of electrons. In fact, in most cases, when we are in organic chemistry, every time you look at oxygen, look at lone pairs of electrons. Look at an electron-rich species because it has a lot of redundant electrons. So I'm bringing my water molecule here, I'm calling it OH2, and I'm saying this oxygen has lone pairs of electrons. These lone pairs of electrons are going to spark off and attacking the carbon with a positive because this is electron-rich. This, because it is positive, is electron deficient. So the electron-rich will always attack the electron-deficient species. So what will happen? This will establish a bond between oxygen and carbon. So that is going to be CH3, CH. Now this is going to be O, then CH2, Cl. Now this oxygen has come with two hydrogen atoms. So I can put one hydrogen atom here, I put the second hydrogen atom here. But because now oxygen has established an extra bond between oxygen and carbon, it is going to become positively charged. It's going to become positively charged. Why is it positively charged? Because it has forced itself to give out a few of its electrons, and therefore it has become positively charged. In order to eliminate the positive charge, what is going to happen is that the oxygen will be forced to cut off one of the hydrogen atoms. Do you see that? So that it can go back to having two bonds. So we can break off maybe this one. The bond will be broken off and it come back to oxygen in an attempt to neutralize the positive there. Being careful, there are some students who break the bond towards hydrogen. If you put this arrow like this is wrong. Why is it wrong? Because this bond cannot go along with hydrogen. Hydrogen is very less electronegative, and because of that, it cannot go along with what? With the bond. It cannot go along with the bond. So by default, the bond will come back to what? To oxygen. The bond will come back to oxygen. So we shall lose the hydrogen. We shall lose the hydrogen. So we shall end up forming CH3, then CH, OH down, then CH2, Cl, CH2Cl. When you look at this compound, what would the name be? What would the name be? Because of the OH now attached, we are going to call it an alcohol. We are going to call it an alcohol. But this alcohol has a chloride. So if we are to give a name, I will give this carbon number 1, carbon number 2, right? So it will be 1 chloro. You look at that. 1 chloro. Now this one is an alcohol. But since it has 3 carbon atoms, it will be propane. The OH is the carbon number 2, right? Propane 2O. propan-2-O. I put this propan-2-O. 1 chloro-propan-2-O. So that is the compound that we have formed here. The chloride is the carbon number 1. The hydroxide is the carbon number 2. You see that? So this becomes 1